discuss about dynamics of rotational motion about a fixed axis. So let's say we have an extended body here. This is extended body, and this body is rotating about this axis. Let's say this is x axis, this is y axis, and this body is rotating about this z axis. Now, if we are taking a particle at point P, let's say here, so this particle will make a circular path about this axis, as we have discussed several times. This circular path is in xy plane. Okay. Then let's say this is center of this circular path which is lying on this z axis, and if we are choosing position vector for this point, let's say this is point P1 and this position vector is R1. Now, if this position vector is making angle theta with x-axis, that is, look, this is x-axis. So, at this point, let's say this axis will be parallel to this one, and this angle here is theta. Okay. Now, let's say this particle moves from here to a new position. Let's say this is new position, point P2, and then it has covered some linear distance here, and this angle, let's say, is very small angle, means it's very small displacement is here from P1 to P2. We are considering this angle to be d theta. Okay. Now, if there is a force acting on this particle here, and let's say this force is acting as F, okay, this force is F, making an angle phi with this position vector R1. This angle is phi. Okay. So we have torque on this body here, torque on this body at this point. We can write R1 cross F. So we are talking about fixed axis. So we have to keep one thing in mind, that we should consider only those position vectors or only those forces which are going to produce torque along this axis. If there is any torque making some angle with this axis is not going to be a fixed axis. This will start rotating. So for that reason, we have to keep only those forces or those position vectors which are contributing a torque along this axis only, so that we can stick to our this consideration. Now consider this is position vector R2. Second one, this one, position vector is R2. And we know this is a circular path. So position vector R1 and position vector R2 will be equal in magnitude. And let's say the angular displacement here is very small. This is d theta. Soon you will come to know what I am trying to do here. This is d theta. And torque is tau. Let's say torque is tau. So tau into d theta, it should be equal to the small work done while moving this particle from point P1 to P2. This is a small work done. And now if you want to know what is total work done, we have to integrate this thing. So that is the part of later discussion. Now, if we are discussing about angular velocity here, so angular velocity point at point 1, when particle is at point 1, is not going to be equal to that of at point 2. And why I am saying? Because there is a torque in action, and this torque is going to change this angular velocity here. This is one thing. So there will be an angular acceleration, and let's say we are talking about constant angular acceleration. So this is constant. So now we have position vector, angular position, and we have angular velocity, we have angular acceleration, we have, of course, angular momentum also, so that we can try to find out. Okay, let me make some space here. Okay, so angular momentum Look, if angular velocity is going to be changed, angular momentum is also going to change. So at this point, point P1, if angular momentum is L1, then it is not going to be equal to the angular momentum at point 2, that is L2. This is one thing. Okay. Now, what about velocity, linear velocity? So at point 1, linear velocity is something, and at point 2, it is something different because of this force. This force is going to give a change in this linear velocity as well. Okay. Now let's say that while moving from point P1 to P2, the time taken is very small time dt for time being. Okay. Then power delivered at point P1 will be, this will be dw, that is work done here, by dt, and then we can write it as tau d theta by dt. Why I am saying that? Because we are taking time derivative both sides, and this angular, this torque is actually constant here. So in that case, we can take it outside, and then we will have this much. This is power, instantaneous power, when the particle is at point P1 and it is trying to move at point P2. Now, we can further continue this discussion. So this power will be tau, and d theta by dt will be instantaneous angular velocity at that point. So we have another thing here. Okay, now let me make some analogy here. Look, we know that power equals to, in case of linear motion, force times velocity, when this force and velocity are making an angle of 0 degree. So these two are in the same direction. In the same way, if this torque and this angular velocity are in the same direction, we can say power is tau times angular velocity. So this is kind of analogy for this. And here we have already mentioned this thing, that this is kind of dw in case of linear motion will be constant force times a small displacement. So another analogy here. And what about this one? This one, no need to write analogy because this is a kind of definition for torque. Okay, now let us move to the next stage of our discussion. Here, most of the physical quantities are vector quantities. So I'm going to explain their directions in this particular case. So let me draw it again in a cleaner way. And let's say this is the movement of the particle. Okay, and this is center about which it is moving. So if it is coming from point P1 to a new point P2, and then it is covering some angle theta, or maybe we can take from here also. This is x-axis, this is z-axis. So if this is angle theta, look, so here in this case, if we apply that right hand rule to obtain what is the direction of this angular displacement, so we have to apply that right hand rule. And if we are doing that, we have to place the four fingers along x-axis, and then we have to curl it towards this position vector r1. So we can get the thumb indicating the direction of this angular displacement. So we can write here that angular displacement is towards positive z direction, or along the positive z direction. Now, what about angular velocity here? In the same way, if this body has angular displacement along z axis, it should have angular velocity along the same axis. Only then it will be in accordance with this displacement, because the direction in which this particle is moving, it will cover distance, or it will cover angular displacement here. So these two should be along the same direction. Now, what about torque? So in this particular case, we are going to take the perpendicular component of this force only, means perpendicular to this position vector. Only then it will give us a torque along this axis. So in that case, what we can do, look here. So we are going to take a perpendicular component of this force. So you can find out what is the direction of torque in this case. And the same way, if you want to use the right hand rule, you can say that torque is along the positive z direction. And now what about angular acceleration? So we can guess from here. These two things are along the same direction. So if torque is acting along the positive y direction, the acceleration, angular acceleration should be along the same direction. So here angular acceleration is also along positive z direction here. Now, if it is speeding down, means slowing down, you can say it is slowing down. That is, torque is not along the positive, rather it is along the negative z direction. The angular acceleration will be also along the negative z direction, and that will slow down this angular velocity, as it happens in case of linear motion. Okay, so let's continue our discussion. Next point. Now we can move to energy part. So we know that the work done will be the change in kinetic energy here. So let's say initially if it was at rest, so the kinetic energy will be I omega square divided by 2. If this particle is at rest initially and then it comes to point P1, and up to there this particle has gained some angular velocity, let's say omega, then we can say kinetic energy will be I omega square by 2, which is equal to work done here, W. Now, what if we are going to take time derivative? That is dw by dt equals to d dt I omega square by 2. And now look, this is power as we know, and this should be torque times angular velocity as we have derived already here. Look, here we have derived. Now, what about this second term? We can write it as I is moment of inertia, and moment of inertia is independent of time. So, this will be I divided by 2, and then we have to obtain for this one. So, this will be 2 omega times d omega by dt. And how can I do that? So, I can do it in this way. Omega square is a function of omega. So, we can use this chain rule. So, d omega by dt can be written as d omega square by dt can be written as d omega square by d omega, and then d omega by dt. This thing we can write. So this will be 2 omega and then this term. Now we know this I omega and we know this part d omega dt, that is angular acceleration. And then we will have here tau equals to I alpha. And we know this thing. This is nothing but Newton's second law in case of rotational motion. So here we have in case of linear motion. This is analogy for the same in case of rotational motion. Okay. Now let me generalize the situation for work done. So in general, if we are talking about work done by a torque, so we have already dw equals to tau d theta. So moving from theta 1 to theta 2, and this torque is acting constantly during this journey. So we will have this work done as dw integration of dw theta 1 to theta 2 and tau d theta. So we can write work done equals to tau theta 2 minus theta 1. And here we have considered that this torque is constant. One thing is here. Now, what about when this torque is not constant, means it is varying with theta, then we have to write it in the functional form here, whatever it is, and then we will have to continue accordingly, or we have to integrate this thing accordingly. Now, coming to example 6.12. So here we have example 6.12, and what is it saying? A cord of negligible mass is wound around the rim of a flywheel of mass 20 kg and radius 20 centimeters. So let's say this is flywheel. This is a kind of heavy disc, mostly made up of steel or some other heavy element maybe. So this is flywheel and a cord of negligible mass is wound around. Okay, so let me try to make this thing. Let's say it is wound around this, and let's say it has an end here. Okay, mass of this wheel is mass of this wheel is 20 kg, and the radius of this wheel, let's say this is radius, this is 20 centimeter, and a steady pull of 25 Newton is applied on the cord as shown in figure 6.31. Okay, I am drawing it for you here. So let's say here the force is 25 Newton, and steady force means a constant force. Now what we need to find out? Yes, the axis of rotation is horizontal. So let's say this is axis of rotation which is horizontal. So let's say this is x-axis here, and this is z-axis, and this is, let's say, y-axis. Okay, so now we have to compute angular acceleration of the flywheel. So angular acceleration, we have mass, we have radius here, so we can find out moment of inertia, we can find out I, and this should be mr square by 2, as in case of solid disk we have this thing. So this will be mr square by 2, and this will be 20 into r, we can convert it into meter, that will be 0.2 meter. So this is 0.2 square divided by 2, and this will be in kg meter square. Okay, now we can write this I is 10, and this will be 0.4 actually kg meter square. So we have moment of inertia of this disk. Now what we can have next? Next we can get what is the torque. And look here, this is position vector here, and this is force, and these two are perpendicular. So torque we can find out directly. Torque should be R times F. So torque will be R, which is 0.2 meter, into F, which is 25 Newton. So we can write it 5.0 Newton meter. Okay, so we have to compute angular acceleration. Now we have moment of inertia and torque. So we can apply this equation. Now you will be convinced why we were talking about these all things. So let's get back to this equation. Look, torque is here. We have moment of inertia obtained there. And now we can find out what is angular acceleration in this case. So the angular acceleration will be alpha will be 5.0, or maybe only 5 you can write. So that is a matter of discussion about significant figures and all those things. So just keeping simple these things here. So at the end, we will have here 50 by 4 unit, and unit for angular acceleration will be radian per squared second, and radian we know that it has a kind of length by length, so that can be unitless. Okay, okay, now coming to this part B. Find the work done by the pool when 2 meter of cord is unwound. So this is very simple. Force is given, the constant force, which is 25 Newton, and along the same direction here, this velocity is, because this cord is unwounding along this line. So force and velocity both are in the same direction. So we can write work done equals to displacement, force times displacement. So this will be 50 joule, 25 into 2 meter, 50 joule. Now, about this question, find also the kinetic energy of the wheel at this point, assume that the wheel starts from rest. So we have initial angular velocity here given, that is 0, because starting from rest means initial angular velocity is 0. Now we have to find out final angular velocity. So this will be initial angular velocity plus alpha times t. Okay, so is it given somewhere or not? Let us check. So time is not given. So we have to apply some different approach here. So let's take another approach. We have final angular velocity squared minus initial angular velocity squared equals to 2 alpha into theta. This is angular displacement, and this we can find out. So how can we find out this thing? Okay, from here we can find out easily. Look, this chord is being unwound for a length of 2 meters. So it means its linear displacement, any particle, if we are choosing on this path, so that is moving up to 2 meter, and we can find out the corresponding rotation of the wheel in radian. So we know that. How can we find out that? So we know that theta equals to L by R, and L is given 2 meters and R is 0.2 meter. So this theta will be 10 radian. Okay, here we can write radian per square second also. No need to worry about that. Now we are able to apply this equation here. So initial angular velocity is 0 given here. So omega square equals to 2 times alpha. What is alpha here? This is 50 by 4. So this is 50 by 4 and times theta, which is 10. And we can write here, look, this is going to be 10 times 2, 20, and divided by 4. Ultimately, we can write it this much. Now, kinetic energy for this rotation will be 1 by 2 I omega square, and this is 1 by 2 I we have obtained here 0.4 kg meter square times omega square. Omega square is here 250. And look, this is energy, so ultimately it will be in joule. So now we can obtain here, this will be 4 into 25 by 2 joule, and ultimately it will be 50 joule. And now we can see, this kinetic energy gained by the flywheel is equal to the work done. Where is that work done? We have obtained, yes, here. So this kinetic energy gained by the flywheel is equal to this work done by this force, which is pulling the string here, or maybe whatever is this. What is this? This is cord. So it is like a string, a strong string. Okay, so this kinetic energy, whatever kinetic energy it has gained, is equal to the work done. And this is showing the relevance of work energy theorem in this rotational dynamics. So this is all for this video. In the next video, we will study about conservation of angular momentum, and that will be the last part of this system of particles and rotational motion.